Hello, everybody. Um, so let's get through this. It's going to be a quicker video. Um, we are covering two sections in this small little video, 8.1 and 8.3. So the title of this chapter, I mean, it's a complicated title, but the title should be confidence intervals. Confidence intervals. Intervals. And what we want to say is basically give an educated guess of some parameter. And remember, a parameter is something that describes a population, mu, sigma, p. So we'd want to say something like, hey, mu is between some number 1 and number 2. Sigma is between some other number 1 and number 2. And then maybe p is between some number 1 and number 2. That's the goal of confidence intervals. Saying with some confidence that we can do something like this, right? And we're going to focus on these two styles. We don't tend to deal with sigma because honestly, there's no fun calculator button that tells us that answer. It's just a lot harder, basically. So we're looking at confidence intervals, and there are general steps, right? The general steps are would be step 0, check conditions. One, we're going to find the interval. And then 2, write a conclusion. And that conclusion usually looks something like, we are 95% confident the blank is between blank and blank. And the blank that goes here is the parameter. In words, right? So if we're trying to find average height of Chapman students, I would say we're 95% confident the average height is between this number and that number, right? Some number 1 and number 2. And you can see there's still conditions, right? Those conditions are the same as before. We're still all based upon a normal distribution, right? And since we're based on a bell-shaped normal distribution, that 95% confidence should ring a bell. And we're going to address that later. So we move on. So again, our goal, estimate the parameter, find this interval. Say mu is between this and this. The proportion of people that are Democrat or the proportion of people that are Republican is between this and this. Well, I can't ask everyone. It's just way too much. It's way too much. Right? But I need a jumping off point. I need a start off point. So our initial guess is called, so this is a definition here. The initial guess for an interval, don't underline that, for an interval, put that in quotes, is the point estimate. It is the point estimate. So basically, I need to figure out, hey, I know I can't ask everyone, but maybe let's ask some people and get a general idea. As long as I'm random, as long as these people are random, then I should be more or less correct. Right? If I ask, 100 random Chapman students. Hey, what's your political affiliation? Let's say I get 60% Democrat. Is that going to be perfect for the school? No. But it's got to be pretty close, right? So I call that my initial guess, no problem. So here's a fact. The point estimate for mu, right? My initial guess for mu is X bar. And my initial guess for P, right? Mu is population mean, X bar is sample mean. I'd ask a sample and find their mean. So what's the sample proportion? Hopefully, we all remember P hat. So that's our initial guess. Okay. So now let's try to say I'm trying to find the average height of the school. I go, okay, so I ask 100 random people and I get the average height is 56 inches. Or let's say 66 inches, 5'6", right? 5'6", 66 inches. Well, I'm not going to be exactly correct, so I give myself some cushion on either side, right? I would go up a certain amount and down a certain amount. Same thing with P. I go up a certain amount and down a certain amount. That cushion, that room for mistakes is called the margin of error. Definition. The room for mistakes this is loose termed, or cushion on either side of the point estimate. Because, I'd go up 6 inches and down 6 inches, or up 10% and down 10%, just to make sure I'm correct. On either side of the point estimate is the margin of error. Okay. Okay, well, again, I could just randomly find a margin of error, right? Again, I ask Chapman students, hey, 100 random Chapman students get 60% are Democrat. I can be like, okay, well, the amount of Democrats at Chapman is somewhere between 50 and 70. And that's a fine answer, but could I do better? Can I bring that in? Can I be more confident? Because it's easy to be 100% confident, right? I can say, oh, okay, well, it's between 30 and 90 for sure. 30 and 90% has got to be the number of Democrats. Same thing with height. It's between 5 foot and 7 foot. Definitely. Definitely. The average height is somewhere between 5 foot and 7 foot. But I need to bring some science in, some reasoning in. Right? So 100% confident isn't really possible because it's possible, but it's not meaningful, because then my margin of error would be way too big. So I bring it in and I'm like, hey, what if I want to be 95% confident? And 95% should ring a bell, especially from test one, right? 95% is 2 standard deviations away. So that's how we're going to measure things. We're going to measure the number of standard deviations times the standard deviation. So here's the fact. The margin of error is given by the number of standard deviations times the actual standard deviation. right? If my standard deviation is 3, then I go up 6 and down 6. If my standard deviation is 0.02, I go up 0.04 and down 0.04, something like that. So that's all fine there if I want to be 95% confident. But what if I want to be 93% confident or 99% confident? I don't have a nice, neat number. So like that 2 standard deviations might turn into 1.7 standard deviations or 2.3 standard deviations or something like that. So I formalize this by saying, so I say more formally, margin of error equals Z alpha over 2. We should have known it was a z-score, right? A z-score measures the number of standard deviations. We'll talk about that alpha over 2 times sigma sub something. Maybe x bar, maybe p hat. Right? It could be either of those. Sigma sub x bar, sigma sub p hat. Something that we know how to deal with. Okay, so let's what the hell's alpha? What the heck's alpha? Let's deal with this. So the idea is if I want to be 95% confident, that is alpha. Well, if I want to be, let's just say 80% confident and I'm normal, I know this is 0.8. And we've done this before. On the outsides, we know is 0.2. And that's what alpha is. Alpha is on the outsides. So, given a confidence level, alpha is the leftover percent in decimal form. Right? And we've actually found alpha before, right? Hopefully we found that on test 2. We didn't call it alpha. Maybe we should have, but it's okay. So as an example, find alpha for the given confidence levels. Okay, well, I'll make a C level here. I'll make an alpha list here. Let's do the common 95%, 90%, 99%, 80%. Maybe you'll see 98%. Those are really the usual ones. So what are the corresponding alphas? So we just talked about 80%. We said that was 0.2 because when I drew the picture, I can see 0.2 is on the outsides. So for 95%, hopefully you can see this. It's 0.05. 90%, 0.10. 99%, 0.01, and 98%, 0.02. And then what you might have started to realize, if alpha is on the outsides, then this bottom bit is alpha over 2. And the top bit is also alpha over 2. And the z-score actually is right here, z alpha over 2, z alpha over 2, with a positive and a negative. So that's how we're finding the z-score. We're drawing this picture. We don't have to draw that picture every time, but that's what it is. That's going to tell us the number of standard deviations. If I want to be this amount confident, find the z-score. So as a little fact, we get to say that Z alpha over 2 equals the absolute value. There's an absolute value sign. So if it spits out a negative number, use the positive version. Normal dist 0, 1, since it's a z-score, dot inverse CDF alpha over 2. Because remember, it's the area to the left. And I look at the picture, area to the left. And that equals that. So you'd get that there. So I believe in you. I know you can practice this on your own. I'm not going to do a specific example there. But basically, we got the whole chapter done right now. Because now I know how to find a confidence interval. So here's this fact. The general formula for a confidence interval is given by the point estimate, the initial guess, plus or minus your margin of error. And now more specifically, we have for mu and for p, right, that's the guess. We're going to estimate mu and p. That's like the whole point here. Here's what we're going to do. We're going to say, first off, check conditions. N is greater than 30, or it's given normal, or there's a new one that we'll address later. No outliers in box plot. But then one would be X bar plus or minus, right? We're finding the interval. I guess we should write it like this. Find interval conditions. Mu is between some number 1 and number 2. X bar, and leave some space, right? This to the left. X bar plus or minus Z alpha over 2 times sigma over square root of n. Because remember, that's sigma sub X bar. I'm going to put an or here. And then the last step is conclusion. So the conditions here for P, hopefully remember, is NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. And then for step 1, we're going to find the interval. P is between some number 1 and number 2. We don't know P, right? And then we say P hat plus or minus Z alpha over 2 times sigma sub P hat, which is square root of P1 minus P over N. put an or here. Then 2, we write a conclusion. So we can find that formula by hand every single time. But we tend not to do things by hand when we have Excel and ClassCalc readily available for us. So what we have is, in ClassCalc, you get to use Z interval, or 1 prop Z interval. And if nothing else made sense, this is what we have to pay attention to. This is where it works, and this is what we'll practice when we come to class. So mu, everything looks good. Estimating mu, finding the confidence interval for mu, that's fine over there on the left side. But for p, there's some suspicion. I don't know p. I just said that right there. But look at my conditions, np, n1 minus p. That doesn't work. So we make a small adjustment. P hat, p hat. And we have to make the same adjustment down here. P hat, p hats. No big deal. Call it a day. But we'll start with these steps on Tuesday. So without further ado, have a great weekend.